Welcome back, students. Let's resume our discussion on integration by substitution. In the first video, we went through some theory part, and then we went through one motivational example very slowly. Now let's speed up a little bit. We're going to stick to equally as simple examples, but a little bit more quickly. So let's go over to the second example. First one we already did. And please note that this is a composite function, and it is very easy to see which is the inside because we have the big parenthesis. And then the differential part. Oh, by the way, the proper name for this dr is not the derivative, it's called differential. Not the derivative. And it's just a name, so if you don't remember, we'll simply say dr. It's okay. Okay, let's get some other character. For x I use y, for r let's use s. S equals r cubed over 9 minus 1. Okay, and let's take the derivative. Three r squared over 9. Of course, you can simplify, so you get r squared over 3. So therefore, ds is equal to r squared over 3 dr. Finally, dr is equals to 3 over r squared ds. And this is the differential part, and then this is the original substitution. Please note the color coding. Alright, shall we put everything into this integration? Let's do that. The red part, that's s, and then the blue part, like that. And what's the resulting integration? Do you see a cancellation? This r squared and that r squared over there cancel each other out. Please note that we have 3 s to the 12th power ds. It's an easy computation. 3 over 13 s to the 13th power. And that's the same as 3 over 13. We need 13th power, and the inside should be the original substitution. Here goes the full solution. Of course, if you open up this cell, you have a little bit better expression. We don't have to keep both solutions, so let's remove that and let's go back to this. Pretty clear what is the inside. We have big parenthesis, so that's your initial substitution. The derivative computation, and then you can substitute dr with respect to the other and plug those back in. Second substitution here, red goes to red, blue goes to blue, and after simplification you get much simpler integral. In the end, you put in the original substitution back in, you get the answer. Can you duplicate this for the other problems? Okay, let's go ahead with this one. This time, let's do it even more quickly. The denominator is an obvious choice for your substitution because numerator you can separate, denominator you can't. So there you go. We have two things to substitute, the inside and the differential. So let's take appropriate character. Let's say u is equal to y squared plus 2y. Derivative y 2y plus 2. So du is equal to 2y plus 2 dy, and finally dy is equal to 1 over 2y plus 2 du. Now, this is the differential part which I'm using blue to highlight, and this is the original substitution. I'm keeping red for this one. Ready? Let's put everything in. This is my u, and my du will be this one. Okay. So, do we have simplification here? This y plus 1 and then this 2y plus 2. If you look carefully, we have simplification because we can factor this 2 out from here. And then this y plus 1 and that y plus 1 cancel each other out. In the end, this is what you get. 1 over 2 u du, or let's write it like this, 1/2 u to the negative first power. Okay, let's apply the antiderivative rule. Antiderivative, this is log. Equivalently speaking, 1/2 log of y squared plus 2y, and there goes the full computation. We have the answer key right over here, and let's see. In my computation, I inserted one more computation here, one more simplification, u to the negative first power. And I really encourage you to do this. Take an extra step, but make sure you have negative first power, because I see this kind of mistakes a lot. 1 over, say, and students are so focused into 1 over something, write it as like this. I see this kind of answer a lot. Whether this is square root, and then you just have this square root like that. Whatever we have as a fraction, put it into log. None of this is right. It works only when we have negative first power. Okay, let's go to the next problem. This one is a little bit harder because we have trigonometric functions, and also we have another reason for that, which I'm trying to emphasize. Okay, initial substitution. What if we take the entire denominator as my substitution? Let's go ahead and do that. We have done that before previously, so why not this time? So square root, so equivalent to 2 plus cosine of x to the 1/2 power. Therefore, the derivative is 1/2 and 2 plus cosine of x, negative 1/2 power, times, by chain rule, you have to multiply the derivative of the inside. And then so on and so forth. Wow, this is a challenge. You see, the whole purpose of this integration by substitution is to simplify. And this is not really helping, it's making worse. And is this a really wrong method? Not really. If you do it right, and if you do carefully, and if you pay for the price of doing it in a little bit harder way, you cannot get it right in the end. Yes, it's a little bit more difficult, but you can do it right. But then again, if there is much superior method, why would we bother doing this? Let's talk about a little bit better method, and also let's discuss how to find that better method. Let's just go to conclusion first. It's better to take the inside of this radical. And we already used up u, so let me use some other character. Y as 2 plus cosine of x. And consequently, the derivative is therefore dx is 1 over negative sine of x dy. So this is the original substitution, isn't it? And then the derivative computation yields the substitution for the differential part, and we are ready to substitute in. And is it gonna be better? Well, number one, so far the computation is easier so far. We didn't have to use this chain rule and things like that. Also, please take a look at this. This y equals to, why do I have black here? Y equals 2 plus cosine of x. So this one here is y. And how about this dx? We can simplify like this. And please note the sine of x in the numerator and the sine of x in the denominator cancel each other out. What do you have in the end? We have 1 over square root of y dy, negative of that to be a little bit more precise. Now this computation is certainly better than the other computation. Kind of pointless to keep these, so let's remove this. And there are a couple of criteria here. Number one, if you see radical inside the denominator, don't consider this as fraction function. This is actually a negative 1/2 power function. You see? This 1 over square root of something, say w, is actually w to the negative 1/2 power function, not reciprocal of square root of w, you see? So it's a lot better to use the inside of the radical rather than the denominator. And that's criterion number one. The second criterion number two, is related to this derivative. You see? Let's go back to this reversed chain rule. This is where everything began, the chain rule, okay? And upon changing the characters, we get this intermediate form. Small f becomes capital F, and then g becomes y, okay? And then upon taking the antiderivative of both, we get this, which is the reversed chain rule. Now, please take a look at this. We have the composite function part over here, and yes, oh come on, okay, successfully highlighted this inside. That's what we had been focusing upon, which I highlighted in red, but also there's another component here, dy dx, the derivative part. So in order to use this reverse chain rule, we need to have the derivative of the inside. Now let's go back to that problem. Inside is 2 plus cosine of x. Here, in this integral, do you have the derivative of the inside flying around? Yes, I do. Sine of x. It's right here. The derivative is negative sine of x, but negative you can always put outside this integral like this. So it's okay. The essence is sine of x, and indeed it's flying around, so that this and that cancel each other out. So that's the second criterion. It's a little bit harder to see the second criterion, but it'll become necessary. If you go over to a little bit harder problem down here, definitely it's going to be more important. Well, we got up to here, so let's finish this computation, okay? So negative of this fraction, so negative of log of that, plus c, so negative of log of square root of 2 plus cosine of x. Is everything right? No, not really. Something is wrong. Well, I wish this were the ordinary class in class so that I can wait indefinitely so that somebody can correct me here. This is video lesson, so I have to give you the answer. This is not going to be a log function because this integral, it may look like a reciprocal function, but no, not really. This is y to the negative 1/2 power function. Therefore, the antiderivative is negative, negative, positive 2 y to the, no, we need negative sign. And consequently, negative 2 square root of 2 plus cosine of x plus c. And there goes the full computation. We have the full computation here as well. That's a little bit better. We don't need duplicate answers, so let's remove this. And then please take a look at this. We have initial substitution, derivative computation, and then work out the differentials. Plug those in and simplify. We have y integral. Don't fall into that step of reciprocal. This is actually a negative 1/2 power function, so the power rule applies, and then we have the final answer. Looks like we'll have to do the final problem in the next video. It's okay, we'll do it. See you soon.